So previously we have defined the determinant for 2 by 2 and how to multiply the matrices. And also we have done something about the matrix multiplication, etc., etc. So let's review something that we can represent matrix A by its element Aij. So for example, if A is 1, 2, 3, 4, then A11 is 1, right? So the first index is called row index, second index for the column. In Korean, I think row is hang, and column is 열, right? A12 is the first row, second column is 2. A21, second row, first column is equal to 3. A22 is equal to 4. Say B, 5, 6, 7, 8. And we can represent B by Bij. Then B11 is 5, B12 is 6, B21 is 7, B22 is 8. Am I loud enough, or you can hear me? No?
No.
Let me see. Hello? No? Can you hear me well? Better or no? Better? You're welcome. All right, but you can at least you can see that, right? So I'll try to speak as loudly as possible and as slowly as possible. If you cannot hear me well, just raise your hand. So if you multiply by matrix A and B, if we want to find the ij's element, let's take 1 to 2, A, I, K, B, K, J. So this is the symbolic notation for the matrix multiplication, and probably you should be familiar with this notation. So according to this, A, B, 1, 1 is, according to K equal 1, 2, 2, A, 1K, B, K2, K1 is A, 1, 1, B, 1, 1, A, 1, 2, B, 2, 1. So this is actually the following way, 1, 2. So A11 is 1, B11 is 5, A12 is 2, B21 is 7, right? So 5 plus 14 is 19. But probably because most of you might have learned the matrix multiplication during your high school days, right? So you probably know the basic rules, but you can just write it down in this way. Transpose is you just replace the row by column and column index by row index. So if you have transpose ij is a ji. AJI. So if A is 1, 2, 3, 4, A transpose is, you just change 1, 3, 2, 4. So A is generally n by n matrix. The simplest case is n is equal to 1, right? A is simply just number. In this case, determinant A is simply just A. N is equal to 2. A1, 2, A2, 1. If n is 3, how to calculate determinant A? So that is the topic for this class. If n is 3, 4, 5, 6, etc., etc., how do we calculate? So in order to do that, we define the few terms. Minor matrix. So Mij is a determinant over matrix obtained by deleting ith row and j's column. I think I put the other way around. J of the original matrix. So for example, A11, A12, A21, A22. Determine minor 1, 1 is a determinant of a matrix obtained by deleting the first row and first column is this, right? So this is A22. M12. M12, you delete the first row, second column, it's A21, right? M21, you delete the second row and first column, you obtain this, A12. M22. M22 is, you delete the second row, second column, you obtain A11. So once you obtain the minor matrix, you can define the cofactors. Cij is defined by minus 1 to the I plus j times mij. So for, say, A, this is the original matrix, A11. Okay, I think I did that. So C11 is minus 1 to the 1 plus 1, M11. Minus 1 to the 1 plus 1 is minus 1 to the 2, right? That is plus 1. So simply A22. C12 is minus 1 to the 1 plus 2, M12 is, what is minus 1 to the 1 plus 2? This is minus 1 to the 3, right? It's minus. It's minus A21. C21 is minus 1 to the 2 plus 1. M21 is minus A12. C22 is minus 1 to the 2 plus 2. M22 is A11. So this is a useful result, so maybe I'll just copy. Is let's compute some interesting things. For example, since already we have this, and A is A11, A12, A21, A22. Let's do some interesting sum. K equals 1 to 2, A1K, C1K. A11, C11, A12, C12, right? That is A11, A22, A12 minus A21. What is this? This is determinant A, right? How about 4 different sums? A2K, C2K. A21, C21, A22, C22, right? That is A21, C21 is minus A12, A22, C22 is A11. This is, okay, determinant A, right? How about let's exchange the index. AK1, CK1. A11, C11 plus A21, C21. This is A11. C11 is A22, right? A21 minus A12, right? This is okay? Determinant A. How about, this is obvious, but let's just do it. AK2, CK2. A 1, 2, C1, 2, A22, C22 is minus A12, A21 plus A22, A11 is determinant A, right? So we have the following result. That is K equal 1 to 2, A IK, CIK is determinant A, right? I는 1, 2. Or AKI, CKI is again determinant A, right? I는 again 1 and 2. Right? So determinant can be represented by two factors. Am I going too fast? All right. How about if the first index for A and C are different? Let's check what happens. A11, C21 plus A12, C22. This is A11, C21 is minus A12, right? Minus A12 plus A12, C22 is A11 is equal to 0. So we can generalize this such that K equal 1 to 2, AIK, CJK is either determinant A when I equal to J or 0. When I and J are different, they are 0, right? Or likewise, AKI, CKJ is determinant A or 0. And I and J are the same, and I and J are different. So we are going to introduce one very useful function called delta ij, which is 1, 0. It has a name, Kronecker delta. Then, using this simple function or notation called the Kronecker delta, by the way, I uploaded the previous class on YouTube. Anybody has checked that YouTube? How many of you have checked? I put my previous class on YouTube. And how many of you have checked? Raise your hand. Okay, you can find my class on YouTube. Under my ID is Professor David An. And if you just type the search word for engineering math, then you can find all my classes since 2019, up to 5 years. So I put my class on 2 weeks ago, so you can check my class, the previous class on this YouTube. So delta ij and AKI CKJ is determinant A delta ij. And we have seen that when determinant A is non-zero, the inverse matrix was defined by the following way, right? A determinant A22 minus A12 minus A21, A11, right? That is actually determinant A, C transpose. And C is a cofactor matrix. For n is equal to 2. So at least for an 2 by 2 matrix, we can define the determinant A from the original matrix element with the cofactor matrix element. And also we can define the inverse matrix by calculating the transpose of cofactor matrix. And actually, this is true for all n. This is a very important statement. The definition of the determinant and definition of the inverse matrix is actually true for all n. Even though I just showed that it's only for n equals 2 case, but this is true that for all n. So this part you need to have a face. So actually, if you take a linear algebra class, maybe linear, then you spend maybe about at least 1 week to show that this is true. But this is more like a compact class. So let's just have a face, right? So this is true for n. So mathematics should be a bit different from the religion, but some part. Of course, you can prove that, but maybe you need 2 weeks. And you don't want to do that, right? No. So let's just believe that this is true for all n. Then let's try to calculate the determinant for 3 by 3. So before I move on, any questions? Everybody follows me up to now? If you don't, then check the YouTube and do some review. So let's move on to 3 by 3 matrices. So determinant A is defined by following summation. K equal to 1, 2, now 3. So A1K, C1K, right? That is A11, C11, A12, C12, A13, C13. So C11 is minus 1 to the 1 plus 1 M11 is the determinant of the matrix obtained by deleting the first row and first column, which is this and this, right? So this is actually A22, A23, A32, A33. A22, A33, minus A23, A32. C12, minus 1 to the 1 plus 2, M12, is we have minus sign, and you delete the first row and second column, you obtain this. A21, A23, A31, A33 is minus of A21, A33 minus A23, A31. So you A23, A31 minus A21, A33, right? C13 minus 1 to the 1 plus 3, M13 is 1 plus 3 is 4, so minus 1 to the 4 is plus 1, and you delete the first row and third column, and you obtain this matrix. A21, A22, A31, A32 is A21, A32 minus A22, A31. Probably I would need this, so I'll just make a copy. And next page, paste. I can move one little bit. Let's make it a bit slow. Okay. So according to the definition, the determinant, of course, up to, for this we need the phase, but determinant A, A11, C11 plus A12, C12, A13, C13 is A11, A22, A33 minus A23, A32 plus A12, A23, A31 minus A2 21, A33, right? 23. Plus A13, A21, A32 minus A22, A31. So let's put plus together and minus sign together. So A11, A22, A33, A12, A23, A31 plus A13, A21, A32 minus A11, A23, A32, A12, A21, A33, A13, A22, A31. And let's see if there is any correlations we can find. One, two, three, right? So for the plus, we have 1, 2, 3, and 2, 3, 1. 2, 3, 1, and 3, 1, 2. 3, 1, 2. That is very interesting thing is we arrange 1, 2, 3 and arrange counterclockwise. So 1, 2, 3, 2, 3, 1, 3, 1, 2. All give positive plus sign, right? How about minus sign? 1, 3, 2. 1, 3, 2. 2, 1, 3. 2, 1, 3. 3, 2, 1. 3, 2, 1. That is 1, 2, 3. In this counterclockwise arrangement, right? 1, 3, 2. 2, 1, 3. 3, 2, 1. So if 1, 2, 3 is clockwise, arranged clockwise, it gives minus sign. On the other hand, 1, 2, 3 is arranged counterclockwise, it gives positive sign, right? So we sometimes call odd permutation. One, two, three, and this we call even permutation. One, two, three. Can you follow me? So you can arrange 1, 2, 3 according to the counterclockwise direction. It's called even permutation. On the other hand, if we arrange 1, 2, 3 in clockwise direction, clockwise means 시계방향, counterclockwise is 반시계방향. fix the first index, and if we arrange the second index according to this, then it's plus or minus that. So we have how many terms? 6, right? Let's introduce a very interesting epsilon I, j, k. I and j and k are different and even permutation. Then it is 1. I and j and k are different and odd permutation. It is minus 1, otherwise 0. Then determinant A can be defined as the following. Epsilon I, j, k, A1I, A2j, A3k. So that is actually, we have 6 cases. So epsilon 1, we have 1, 2, 3. This is even. 1, 2, 3, 2, 3, 1, 3, 1, 2 is equal to 1. And other permutation is epsilon 1, 3, 2, epsilon 3, 2, 1, epsilon 2, 1, 3 is minus 1. So when n is equal to 3, then distinguishing this even and odd permutation is very easy. You just arrange 1, 2, 3, and then just look at the order clockwise or counterclockwise, and you will find out the odd permutation versus even permutation. But if n is more than 4, 3, 4, then it's a little bit complicated. So in that case, we need to define what is even permutation or odd permutation. For example, we have 1, 2, 4, 3. How many times you need to change any pair to make it 1, 2, 3, 4? If you change this, right, it becomes 1, 2, 3, 4. How many times? 1, right? 1 time. In this case, we call it odd permutation. So the number of exchanging any neighboring numbers pair is even or odd, then it's called even permutation. Odd permutation. How about 1, 3, 2, 4? How many times you need to? No. How many times you need to change? Just once, right? So this is even or odd? Odd, right? So this is odd. About 1, 3, 4, 2. Twice, right? You need to change this and then change this, right? So twice. In this case, it's called even. So if we have a 4 by 4 matrix, so A11, A12, A13, A14, A21, A22, A23, A24, A31, A32, A33, A34, A41, A42, A43, A44. Determinant A is actually I, J, K, L, epsilon I, J, K, L, A1I, A2J, A3K, A4L. So how many elements are you going to expect? Only 4 factorial, 24. Right? So probability equation, I may ask you to calculate the determinant up to 4, order 4. So you just need to sum over 4, right? So try some, say, 1, 0, 0, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Let's just do it as a homework. And when I say homework, that means you just do it at home. So you don't have to give it to me. Perhaps you can take a break for a few minutes and continue. So actually, this has a name, Levi-Civita symbol. So epsilon, either epsilon ijk, epsilon ijkl is called Levi-Civita symbol. So Levi-Civita is an Italian mathematician of 19th century. So using this notation, we can actually extend our definition of the determinant to n by n. So when matrix A is given by A11, A12, A1n, A21, A22, A2n. So I guess I'm loud enough, right? AN1, AN2, ANN. Then determinant A can be calculated as I1, IN, epsilon I1, I2, IN, A1, I1, A2, I2, AN, IN. That's the most general definition of a determinant for n by n using extended Levi-Civita symbol for n cases. So it's actually true. Epsilon I1, I2, IN is 1, minus 1, 0. Uneven. Odd. Otherwise. I think we can think up to maybe 4. If you can imagine, there's even another condition up to maybe 4 or 5. But other than that, if it's over 5, probably you have to use a computer's program. But that's a very neat way of defining the determinant. So what's the use of a determinant? Why we are learning that? The first usage is solving linear equations. So determinants are very useful, but why we are learning that is to solve linear equations. So use to solve probably I have to replace the tape. It's getting old. To solve the said linear equation. For example, A11 x1, A12 x2 equal to P1, A21 x2 x1, A22 x2 is P2. This is typical linear equation for two independent variables. In Korean, E1 is so we can actually represent by the following way. A11, A12, A21, A22, X, X1, X2, P, P1, P2. This is column matrix. We call cat vector. then A x p, right? If determinant A is non-zero, then A inverse exists, right? In this case, we multiply by A inverse AX, A inverse P. And this is identity, right? So matrix multiplication is associative. So we can multiply this A inverse and A first, which is identity, right? Then X is equal to A inverse P. Very simple, right? So actually, maybe I'm going a little too fast, so I will let you copy. I think I have a tendency to go fast. So if you think I'm going too fast, just let me know. Then I will slow down. Okay. So A is A11, A12, A21, A22. A determinant A is non-zero. A inverse is determinant A over A22, A11, minus A12, minus A21, right? So X is P1, P2, right? So you can actually very easily calculate A22 B1 minus A12 B2 minus A21 B1 plus A11 B2. So actually you can obtain the same result using Gaussian elimination. The first part, say A11 x1, A12 x2 is equal to B1, A22 x1, A21, A22 x2 is P2. So what do? We multiply in order to remove x2 1 times A22 minus 2 times A12, right? A12, then A11, A22, x1 minus A21, A12, x1 is equal to A22 B1 minus A12 B2, right? So A11, A22 minus A12, A21, right? 21 x1 is equal to A22 B1 minus A12 B2. 4 x1 is actually A11, A22 minus A12, A21 times A22 B1 minus A12 B2, right? So this result is same as this. So of course you can show P by 1 linear equations by using Gaussian elimination, but you can also obtain the same result using inverse elimination. And in order to calculate the determinant A, you need to have a determinant. So in general, going a little too fast. I'll let you have time to copy. Even though I have shown that this is only for 2 by 2, you can easily generalize to n by n. So, or maybe I. P1, A21 x1, A22 x2, A2n x equal to P2, A2n1 x1, an2 x2 plus blah blah ann xn equal to pn. Then you can define A matrix as A11, A12, A1n, A21, A22, A2n, N1, N2. Cat vector X, this is name, cat vector. Cat vector is a column vector matrix. The same thing. Cat vector x1, xn, and p, p1, pn. Then linear equation becomes ax equal p. This cat vector notation is used in quantum computing. So in quantum computing, we use a lot of matrices, and single column vector is called cat vector in quantum computer terminology. So I'm using that to make you familiar with the quantum technology, which is actually coming very fast. So if determinant A is non-zero, then X is A inverse P. Of course, A inverse is determinant A of CT. And about 80%, the reason why the linear equation solver is important is the following. %, of engineering problems becomes linear equations. So if you are familiar with the determinant and inverse matrix, then you can already solve almost a lot of engineering problems. That's the reason why we are learning this. But sometimes you need to solve million by million matrices. That takes a lot of time. So we are going to look into more cat vectors. And for now, let's assume that this x1 belongs to complex number. The complex number is A and B are real numbers. I square is -1. It's called complex number, imaginary number. And complex conjugate is called A minus IB. It's X complex, X conjugate. Defined. So I is actually square root of -1. Then X complex conjugate is A plus IB, A minus IB, A square, IPA minus IAB, I minus IB square. This cancels each other. This becomes 1. A square plus B square. And if we take complex conjugate and complex conjugate again, it's original number. So cat vector is a column matrix. We define a new matrix which is a row vector. This is a row matrix, and it has a name called bra vector. Cat vector and bra vector. So bra vector is actually obtained from the cat vector by taking the transpose. Transpose means you change the column by row, right? And then take a complex conjugate. Sometimes we call this adjoint. So adjoint is a transpose with a complex conjugate. So origin of the bracket in English text, this is called what? Bracket. Right? This 가로, parenthesis. This 중괄호, brace. So bra and cat vector actually from this bracket. You just cut it half. So left side become bra vector and right half side become cat vector. This is 1925 English physicist Paul Andrea and Maurice Dirac actually used this notation to define the cat vector and bra vector. So it can actually introduce very interesting the product. This bra vector and cat vector notation may not be familiar to you. So there's one method that you can get familiar with by memorizing. So for example, if x 1, 2, what is bra vector? Simply 1, 2, right? This is real number, so complex conjugate is the same. Say x1, xn, y1, yn. We define inner product. Which is x1 complex conjugate to y1, x2 complex conjugate to y2, xn complex conjugate yn. What happens if you change the order? On the other end, right? Yx. If we change the order, then this is yx, right? So y1, yn, x1, xn, y1 complex conjugate x1, y2 complex conjugate x2, yn complex conjugate xn is actually x1 complex conjugate y1 complex conjugate plus x2 complex conjugate y2 complex conjugate xn complex conjugate yn complex conjugate is x1 complex conjugate y1, x2 complex conjugate y2, xn complex conjugate yn complex conjugate is actually x and y complex conjugate. Let me check. So in the product, if you change the order, then you have the two complex conjugates. I just leave it here. Say, example, x is square root of 1i, y square root of 1 minus I. Then x vector is square root of 1 minus I, right? Y square root of 1i. In this case, very interesting result we obtain. X, y, what do we get? Square root of 1 minus I, square root of 1 minus I, 1 half 1 minus 1 is equal to 0, right? So if the inner product is 0, we say these two vectors are orthogonal to each other. How about x and x? One plus 1 is equal to 1, right? So in that case, we say x is normalized. So when inner product with itself is 1, then you say the vector is normalized. In Korean, I think it's 정규화. I think I'm going a little bit fast, right? Any question? And actually, we are learning another interesting product, the outer product. That is x and y. We write it this way. define just simply x1, y1, x1, yn, x2, y1, x2, yn, xn, y1, xn, yn. So outer product is n by n matrix. And in general, the outer product is actually very important in quantum mechanics too. Quantum mechanics, quantum computing, etc., etc. So for now, let's consider 2 by 2 matrices. Probably most of the engineering mathematics doesn't cover outer product. And neither the linear algebra class. But this is actually very important. Outer product 안 배우지. So it's a very important topic. So let's do some deviations. But another important property of matrix is if A adjoint is A, which is A transpose complex conjugate, is called self-adjoint or Hermitian. Typical matrix is like, let's say, X matrix, 0, 1, 1, 0. X transpose is what? 0, 1, 1, 0, right? And X, because transpose complex conjugate is again same. So X is Hermitian matrix. Let's consider a particular matrix. Lambda 1 lambda 2 1 minus 1, and say lambda 1 is equal to 1, lambda 2 is equal to minus 1. We said. In my class, we are going to use some Greek alphabet. So probably it's better to familiar with some Greek. This is alpha, beta, gamma, delta, epsilon, lambda, mu, nu, tau, rho, sigma. There are 24 Greek alphabet, but probably this will be enough for you to follow my class. So let's play with this simple the matrix and cat vectors. This matrix. Oops. Oh. No product. Root 1, 1, 1, 1 over root 2, 1, 1, which is 1/2. 2 is equal to 1, right? Lambda 2, lambda 2. Square root of 2, 1 minus 1. Square root of 2, 1 minus 1 is again equal to 1. But lambda 1, lambda 2. Square root of 2, 1, 1. Square root of 2, 1 minus 1 is 0. Lambda 2, lambda 1. Again 0, right? So lambda 1 and lambda 2 are orthogonal to each other. And normalized, right? Because the inner product is equal to 1. So we say the set of these two vectors is called orthonormal basis. Orthonormal basis. This is just for 2 by 2 matrix, but actually we can learn a lot of mathematics about that, mathematical properties about this two-dimensional matrices. So one thing is Hermitian matrix say x is 0, 1, 1, 0. We can associate orthonormal vectors, normal basis, lambda 1, lambda 2, such that lambda 1 is equal to 1, 1, lambda 2, 1 minus 1. Some numbers. Lambda 1 equal to 1, lambda 2 equal to minus 1. Then lambda 1, lambda 1, lambda 2, lambda 2 is identity. Lambda 1 is x. It's called the spectral theorem. So next week we are going to learn more in-depth discussion about it. in-depth discussion about structural theory. But for now, let's just assume that for now that, okay, we can choose some formation matrix. And with this matrix, we can associate some orthonormal vectors, lambda 1 and lambda 2, such that lambda 1 is given by this form, lambda 2 is given by this form, and some numbers. So we associate some number, lambda 1 is 1, lambda 2 is minus 1. Then we have a very interesting outer product, that is the outer product of lambda 1 plus outer product of lambda 2 is identity. If we multiply by lambda 1, with this outer product of lambda 1 plus lambda 2, with this is given original matrix. It's called spectral theory. So maybe you can do some more example, because this may be true only for this case only, right? But let's see if this is true for other cases. I think I should make a this is one. We introduce another matrix, C, 1, 0, 0, minus 1. Then this adjoint is same, right? So Z is Hermitian. In this case, we said lambda 1 is 1, 0, lambda 2, 0, 1. Same lambda, plus 1, lambda 2 is minus 1. And let's see. Lambda 1 is 1, 0, 1, 0 is 1, 0, 0, 0, right? Lambda 2, 0, 1, 0, 1. 0, 0, 0, 1, right? Then lambda 1 plus lambda 2 is 0, 0, 0, 1, right? Which is identity. On the other hand, lambda 1, lambda 2 is 1, 0, 0, 0 minus 0, 0, 0, 1 is 1, 0, 0, minus 1 is Z, right? So at least we found that this is true for two cases. So we find some information matrix. Maybe lucky 3. One more example. 3, 4번? What have done? It's okay. I think I put the Z matrix for the empty slot, so I didn't waste pages. Probably I should do this. Equal copy. delete. And this is 3. I don't know. So you have to, I inserted one page and then also made something. So you have to figure it out. How about lambda 1 outer product? This is square root 2 over 1, 1, square root of 2 over 1, 1, right? 1/2, 1, 1, 1, 1. How about lambda 2, lambda 2? Square root of 2, 1 minus 1, square root of 2, 1 minus 1, square root of 2, 1 minus 1, minus 1, 1, right? 1/2. Sorry. And I have said lambda 1 is equal to 1, lambda 2 is minus 1. What happens? Lambda 1 plus lambda 2, lambda 2? One half, 1, 1, 1, 1, 1/2, 1 minus 1, minus 1, 1, right? It becomes 1, 0, 0, 1, which is identity. On the other hand, lambda 1, lambda 1, lambda 1, lambda 2, lambda 2, lambda 2 becomes 1/2, 1, 1, 1, 1, minus 1/2, 1 minus 1, minus 1, 1. It becomes 0, 1, 1, 0, which was some matrix, right, that we considered. I inserted the empty page, and I don't know how to delete this one. Sorry about that. If I change it to PDF, then I can edit that. But I have tried several times. Sometimes I make a same mistake, and there is no command that I can delete this part. So sorry about that. Okay. How about lambda 1, lambda 1? Oh. Right. Then, oh my goodness. This is actually 2. Copy. Where is it? Let me see. there any way that I can make a copy? How about another case? So this is case 4. Say Y matrix. In this case, we have imaginary number. Adjoint. Okay. Probably let's do it slowly. Transpose. 0, I, minus I, 0, right? And you take the complex conjugate. 0 minus I, 0, which is Y adjoint is Y. So this matrix is Hermitian. We associate lambda 1, 1i, lambda 2, 1 minus I. Of course, lambda 1 plus 1, lambda 2 minus 1. Then outer product 1i, 1 minus I, right? Which is 1/2, 1 minus I, 1. Lambda 2 is square root of 2, 1 minus I, square root of 2, 1i, 1/2, 1 I minus I, 1, right? So lambda 1 plus lambda 2 is equal to, they cancel each other. 1, 0, 0, 1 equal to I, right? Lambda 1 plus lambda 2 is 1/2, 1 minus I, 1 minus 1/2, 1 I minus I, 1 is actually 0 minus I, 0, which is Y. So we can see that this is only for 2 by 2 cases, and we have considered 3 matrices, but this spectral theorem generally holds for 2 by 2. And I think we have covered too much detail, right? Already. So what do you think about stopping today? Here. Good idea? I think you need time to digest this material. So see you next week. And I'm going to put the lecture on YouTube tonight.